Hey there, and welcome to this calm, lo-fi explainer. If you're studying late right now, or maybe just trying to wrap your head around some foundational engineering concepts, I want you to go ahead and take a deep breath. You are in the absolute right place. Today, we're going to demystify some basic electrical concepts together. No high-pressure lectures, no rushing through really complex formulas, just a reassuring, relaxed stroll through the fundamental laws of energy. We're going to take what looks like an intimidating page of textbook physics and transform it into a beautifully logical system that honestly makes perfect sense. Let's just start with a super gentle, everyday question. Ever wonder what actually happens when you leave a light on in your room? We flip switches all day long without a second thought. We plug in our phones, we boil water, we open our laptops. Electricity is basically this invisible, silent partner in our daily lives. But what is literally happening behind the wall? Well, before we throw any math or definitions at you, I really just want to spark your curiosity about the energy flowing all around you right now. Because understanding this stuff, it doesn't just help you pass a test, it helps you understand the whole modern world. Okay, so take a look at this snapshot straight from a student's notebook covering electrical power and energy. I know. At first glance, handwritten formulas like P equals V times I or W equals P times T can look completely overwhelming. It looks really complicated, kind of like a secret code. But I promise you, it's not. Let's just break it down. Reassure yourself right now that we are going to walk through this exact logic step by step, completely stress-free. Every single letter on this page represents a really simple physical concept. Section 1. Push and flow. To start making sense of those equations, we need to transition into our first core concept. We're going to frame these mathematical variables not as intimidating algebra, but as simple physical movements. Think of it as push and flow. If you can visualize pushing something and you can visualize something flowing, you already have the mental tools you need to master basic electrical engineering. Okay, let's dive into this first variable, voltage, represented by the letter V. As the notes perfectly define it, electrical potential, or voltage, is the amount of work to be done to move a unit positive charge from one place to another. Basically, think of voltage as the push behind the electricity. It's the potential energy, the effort required to get things moving through a wire. Without this push, absolutely nothing happens. The charges just sit there. Voltage is that invisible pressure that's eager to do the work. Now, once you have that push, you get movement. And that brings us right to current, represented by the letter I. The source material defines it as the rate of flow of electric charge. So if voltage is the push, current is simply the flow. It's the steady stream of those tiny charges, the electrons, moving along a conducting path over time. And it's measured in amperes. So just picture a gentle river. The steepness of the mountain, that's the voltage pushing the water. And the actual water moving past you, that's the current. It really is that straightforward. Section 2. Power, the rate of work. Now, let's see how this builds. Since we understand the push and the flow, we're going to guide these two foundational ideas together into something that actually does work in the real world. This is where those abstract concepts turn into the actual light from your desk lamp or the heat from your stove. We're talking about power. And this beautifully illustrates how simple the math actually is. Power, represented by P, is simply voltage multiplied by current. So P equals V times I. When you multiply the push by the flow, you get power. As the notes state, it is the rate at which work is done. It's literally a measure of how fast those pushed charges are actually accomplishing something in your electrical circuit right at this very second. So the crucial point here is how we measure this active work. The unit for electrical power is the watt, and as the source notes point out, 1 watt is exactly equal to 1 joule of work per second. Think about your study lamp glowing right now. If it's a 10-watt LED bulb, that means 10 joules of work are getting done every single second, continuously, just to keep your page illuminated. It's a constant, active rate of effort. Section 3. Time changes everything. Okay, so we have the push, we have the flow, and we know their combined power. Now we move to the final variable of our journey. We're going to see how simply letting the clock run transforms the concept of power into the concept of energy consumption. This right here is the missing piece of the puzzle that connects your physics notes directly to your monthly electricity bill. It's absolutely crucial to clarify this distinction because, honestly, they get mixed up all the time. Let's use a relatable anchor. Think of your smartphone. Power is the phone's ability to turn on and run its processor at full speed right this second. That's its capacity to do work. Energy, however, is the actual battery drain. Energy takes that power and asks, okay, but how long did you leave the screen on? Energy is the total amount of work done over a specific period. Which leads us right to this beautifully simple equation from our notes. Electrical energy, denoted as W, equals power P multiplied by time, T. That's it. Energy is literally just the power we already calculated, the push times the flow, multiplied by the time we leave the device running. The unit here becomes the joule, or the watt second. If you understand this one single slide, you understand the fundamental math behind all energy consumption. Let's just walk through this procedural calculation one more time, nice and easy. If you ever face a problem about energy, just hold on to this logical sequence. Step 1, find your voltage, the push, and your current, the flow. Step 2, multiply those two together to find your power. P equals V times I. This tells you the rate of work. Step 3, multiply that power by the time the circuit is active. W equals P times T. And just like that, you found the total energy. 3 simple, totally stress-free steps. Section 4. A peaceful final thought. Well, we've covered a lot of ground today, from basic definitions all the way up to calculating total energy consumption. And as we signal the end of our study session together, I really want us to wind down with a grounding takeaway. Let's just step back from the equations for a moment and look at what they actually represent. Looking back at the handwritten notes we started with, there is this foundational concept written out very clearly. Energy is defined as the capacity to do work. When you read it aloud, it almost sounds like a profound observation about the universe, doesn't it? Whether it's electrical, mechanical, chemical, or thermal, energy is simply the stored potential all around us, just waiting for the right circuit, the right path, to be transformed into action. So the next time you leave a light on or plug in your laptop, you're going to know exactly what's happening. You have the voltage pushing, the current flowing, generating the power, and accumulating energy over time. Honestly, isn't it kind of nice to know exactly how the invisible forces powering our daily lives actually work? You are completely capable of understanding this. Keep that sense of calm clarity with you and stay curious.